My name is Ruixin. I'm a fourth-year PhD student from Purdue University. My advisor is Professor Tianyi Zhang. I'm excited to share our paper, Show Me Why It's Correct, Saving 1/3 of debugging time in program repair with interactive runtime comparison. Bug fixing is one of the most challenging tasks for developers. In a recent survey of 950 developers, 44% said it was their biggest pain point. Automated program repair, or APR, helps developers fix bugs by automatically generating patches that makes failing tests pass. However, developers are still skeptical about the quality of APR patches. They need to understand how the bug is fixed, and they need to validate whether a patch is overfitting and compare multiple patch candidates. And an overfitting patch may make all tests pass by chance, but it does not truly address the root cause of the bug. This happens because APR tools may generate too many patches, too many plausible patches. But developers quickly lose confidence if the first few turns out to be wrong. According to the recent surveys, when developers receive overfitting patches, their bug fixing success rate drops by 65%. On average, developers spend about 23 minutes manually investigating and comparing the generated patches before deciding which one is actually correct. This process is indeed very time-consuming. There are several approaches to address this challenge. Patch ranking and classification techniques try to prioritize patches that are more likely to be correct. And patch clustering methods group similar patches together so developers do not have to go through a long list of candidates. Instead, they only need to inspect one representative patch from each cluster. Interactive patch filtering allows developers to answer predefined questions to quickly eliminate obvious incorrect candidates. However, even with these approaches, developers still need to manually debug the program. They must answer the several critical questions before they can finally decide which patch is actually correct. For example, how do the incorrect runtime values originate from the buggy code and propagate to the test oracle? And how does a plausible patch change the program's runtime behavior to fix the root cause of the bug? Now, while the interactive patch filtering approach does ask developers questions to eliminate incorrect patches, the effectiveness is quite limited because there are only a few predefined questions, and for program execution traces, it only allows side-by-side comparisons of two patches at a time. So to bridge this gap, we propose a tool called iFix, an interactive tool that helps developers better understand the runtime behavior of auto-generated patches. The input to iFix is a buggy project, along with a list of plausible patches generated by APR techniques. Like prior work, we also need to reduce the number of patches that developers must inspect, but this is not where our main novelty lies. This approach is called patch clustering and sampling. It keeps the candidate set both small and diverse, and it ranks the patches to prioritize the most promising ones. Our main contribution is called runtime behavior comparison. It runs the fail test with each candidate patch applied and records the runtime values of related functions. It then aligns these results into tables to compare behaviors across patches. Unlike prior work like compares only two patches at a time side by side, it supports a comprehensive comparison among multiple patches. We have implemented this iFix as a VS Code extension. In the next few slides, I will introduce the two core techniques behind iFix. The goal of patch clustering and sampling approach is to help users navigate candidate patch space without feeling overwhelmed. iFix first performs hierarchical clustering to group similar patches together. For each cluster, it selects the centroid patch as the most representative one. Finally, for each representative, iFix ranks these patches to prioritize the correct patch. Building on the hierarchical clustering, we designed a new interactive widget. It lets users navigate the patch space and choose directions based on their preferences for each sample patch. When a sample patch looks promising but not fully correct, right, users can zoom in to explore similar patches within the same cluster. iFix recursively divides each cluster into smaller subclusters until there are no more than 5 patches remaining. When the patch looks completely wrong, users can reject it along with similar patches that are also likely to be incorrect. Now let's move on to the main contribution of this work, runtime behavior comparison. It helps developers understand how incorrect values propagate through the code and how different patches fix those values. This is made possible through several steps of code analysis. First, iFix performs a call graph analysis to trace the function calls from the failing test to the crash location. For example, in this bug, there are 3 layers of function calls. The buggy code in the innermost function eventually causes the test failure in the outermost function. Second, iFix performs a diffuse analysis to extract the runtime values related to the bug. Starting from the bug location, it captures the defined variables, use variables, method codes, and sub-expressions, tracing them all the way down to the failing function, to the failing test function. After that, iFix instruments the source code to log the relevant runtime values. It then creates multiple copies of the code and applies each sample patch separately. Finally, we collect the runtime values from all instrumented versions of the code and aggregate these values into a comparison table. In this table, the same variable at the same line is aligned in one row, and the values are grouped and color-coded for easy comparison, which will be elaborated later. Now let's walk through the user interface. It has 2 main parts. The first one is called interactive patch exploration, which should have been introduced before, and the second one is runtime comparison table. The user can divide into a cluster or similar patches by clicking on the button Explore Similar Patches. And for the table, iFix creates one runtime comparison table for each function in the call stack. For example, the first table shows the buggy function, the second one shows its caller, and the last one corresponds to the failing test. These tables can be collapsed or expanded by clicking on the titles. Inside each table, the buggy variables are shown in red, while the values produced by patches appear in different shades of green. For each row, the same color is used to highlight the identical runtime values produced by different patches. With iFix, developers no longer need to apply each patch, set breakpoints, and repeat the same process, same tracing and debugging process over and over again with different patches. Right? Instead, they can use the comparison table to see the key runtime values, the difference of the key runtime values, and they can identify the root cause of the bug and distinguish the behaviors of different patch candidates. For more details about iFix, please check out our demo video on YouTube. To evaluate the usability, we conducted a user study with 28 participants from both academia and industry. We randomly selected 4 bugs from Defects4j as the bug fixing tasks for our participants. Our baseline is a state-of-the-art tool called Imperfer. It's an interactive patch filtering system. For the patches, we used a learning-based APR. We used the patches generated by a learning-based APR tool called Cure. Unfortunately, this work was started before APR was conquered by LLMs. We aim to answer 3 research questions. First, how effectively does iFix enhance patch validation performance? Second, how much does it boost developers' confidence in auto-generated patches? And third, how does iFix support programmers with different levels of expertise? We recruited 28 participants, including undergrad and grad students, software developers, and research scientists. Most of them have at least 1 year of programming and Java experience, and each participant worked on 3 out of 4 Defects4j bugs And their tasks were divided into 3 debugging settings: manual inspection, using iFix, and using the baseline tool. For each bug-fixing task, participants receive a bug report and a list of candidate patches. Except for the manual debugging setting, they first receive a short tutorial video on how to use the tool. They were also given access to 2 IDEs, VS Code and Eclipse, to help with debugging. And they had 20 minutes to debug each of the programs and choose the correct patch they believe to be correct. After each task, they completed a short survey to share their experience and the feedback. Our results show that compared with manual debugging and the baseline, our tool increased the success rate by 40% and 8% respectively. It also reduced the debugging time by 36% and 33%. These improvements are statistically significant as confirmed by a one-way ANOVA test. According to the post-hack survey, using our tool made participants more confident in patch selection. The median confidence score increased by 50% compared to manual debugging and 20% compared to the baseline. And finally, as the programming expertise increases, the benefits of using iFix became even more significant. Due to time limit, I will only present the key findings here. You can visit our website for more details about the user study. So in addition to the qualitative user study, we conducted a quantitative evaluation to see how good the sampled patches are. We compared with 4 ranking baselines: original, static, learning-based, and similarity-based ranking. We also asked 2 more research questions. First, force. How effective is our clustering and sampling algorithm in prioritizing correct patches? And fifth, how sensitive it is to different APR techniques. In iFix, the ranking of a patch within a hierarchical cluster is determined by the position in the nested cluster architecture. For example, if a correct patch is ranked at index X in level K, and there are N1, N2, and so on clusters at each level along the path, the final rank of the patch is calculated as N1 plus N2 and etc. up to nk-1 plus X. Our results show that this approach improves the ranking of correct patches and generalizes well across different APR tools. And this concludes my presentation. Thank you all for your listening, and now I'd like to open the floor to questions.
Hi, thanks for the talk. I'm curious how iFix behaves when the different patches result in very different call stacks. There may be very different sets of variables in scope. They may have different numbers of frames. They may result in like loops with different numbers of iterations, or recursive calls with different numbers of. How do you handle that?
Okay, so for loops, right? So for loops, we will aggregate different iterations of loops within one cell. So we only record the last iteration. And for recursive calls, now unfortunately we can only show every function calls, but it should be considered in future work, right?
And what if the call stack is just very different? I mean,
okay, for this,
different functions.
Yes. For this, we will display all call stack among the different patches, and for the patches that visit this function but not that function, so the runtime value will be blank. So the users will be able to distinguish the execution traces from the table. Yeah.
Okay. Did that show up in the user study, or
I'm sorry?
Were there cases like that in the user study?
So for the user study cases, there are cases that the execution traces are different, but there are not different functions.
Okay.
Yes.
Okay. Thank you.
Thank you.
Speaker.